Hello everybody. So today I will talk about the geospatial indexes. So in today's video I will talk about the special geospatial indexes like quad tree, R tree, and geohash. Okay, and also I will talk about the use cases of these um, indexes and also, of course, pros and cons of them. That being said, let me get started. So firstly, I will talk about why geospatial indexes are needed. So the typical use case of the geospatial indexes are, let's say, like in Uber or maybe like in Tinder, the user would like to know the other users who are close to him or her. And when I think of that, let's say the user is in California and he'd like to know the maybe driver or girls in the tender who are 30 miles close to him. So in this case, you know the query to the database should be gets all the data points which is up to 30 miles from the point xy or maybe longitude latitude. So that's a typical query. And when I think of this, let's say I store longitude, latitude data in the database. Right. Let's see. Sorry. This. And I'd like to know the point which is close to, up to 30 miles away from this. Yeah, let's make it 3 miles. So this is the kind of data point, and I'd like to know the point which is up to 3 distance 3. So in this case, so one of the quick ideas maybe I come up with is, let's say I get all the data points in this area. And because this is what I get from this is square, I have to filter out the point in the edge, which is inside of the square, but the point from 2030 is more than 3. But when I think of this, as a quick idea, maybe you think that we can use the composite index of, database, like relational database. So if I create the composite index of xy, I would say why this doesn't work. Why creating the composite index with B tree doesn't work. So when I create the composite index, let's say there point like this. So let's say these are the data points xy currently exist in the database. So when I create the composite index with xy tuple, they are sorted in this way, in the tuple. As a tuple, they are sorted and they are put on the leaves of the B tree. The problem here is I can filter this B tree with a kind of binary search with X range 17 to 20 first. But after that, when I take a look at this Y are not sorted. So to get the Y, which is in the range of 27 to 33, which is this, and maybe I will change it a bit. Yeah, maybe they're this and this. I cannot use the binary search in Y, which means that I can use the binary search firstly with log X. I can use the binary search for X, and the time complexity should be log N. But after that, for Y, I have to scan the remaining filtered data points. And in the worst case, it takes the whole scan. In the case, let's say filtering with X doesn't filter that much. In that case, in the worst case, the time complexity is over n. So even with binary tree, B tree, this query cannot be handled, efficiently. So now I explained why the simple B plus tree doesn't work to search the query pattern, like gets all the data point which is up to some distance from center point xy. So that being said, I will talk how these geospatial indexes can handle this kind of query so efficiently. Okay, so I will start with the quad tree. So I will show the picture. So quad tree is a tree structure. So originally the area, firstly, the area is represented by only single node. But let's say there are so many data points in this area. In this area, it's divided into 4 sub-areas. And then, if there are so many points in this sub-area, that sub-area only is divided into 4 sub-areas again. So the dividing the area occurs recursively in this quad tree. And as I can see, when the area is divided into 4, the data point, which was represented by the parent space, is now moved to the child nodes. So that's a quad tree. So I think I can be, easily understandable with an example restaurants in the Yelp. So in the Yelp, there are so many restaurants or businesses, and each of them has the physical address. So you can think of each point as each restaurant or each business. Yeah. So for the dense area like New York City, because there are so many restaurants, that area is divided into 4 many times recursively. So in that case, that area has the deep, the depth of the reef of the dense area is so big. Yeah. And actually that's the kind of, disadvantage of using this quad tree. So I will write it down here. So the dense area, just say, okay. So I should say, the reef of the dense area is deep. The tree is unbalanced. So why this is a problem? Because if I'd like to search if I search the restaurant in the specific area in New York City, internally in database, the query engine has to go down this, tree to, to the reef, which is very deep in this structure. And also, actually, this becomes a hotspot because when there are so many restaurants in New York, many users search the restaurants in New York. So there are many queries which goes down to that reef node in the depths. So in this way, the reef, this is problematic in terms of the performance. Okay. So also, let's say this point is moved to another place. So in that case, what happens is that, you know, this point, so firstly, if it is a small move, the data inside of the node has to be updated. But if there is a big move which goes across the borderline occurs, this point goes somewhere else. And maybe originally this area was so dense, but now then this area may become dense. In that case, I have to rebuild, or I should say restructure the tree structure. So it costs so much. So I can say this code tree is not good at handling the dynamic data. Because of the restructure of the tree. I mean, the cost of restructuring the tree. Okay. So these are characteristics of the quad tree. Yeah, this quad tree is using the Google Map tiling, but actually not so often used in the product like Uber or Tinder. Yeah. Okay, for those systems, actually R-tree and geohash are more frequently used. So I will go to the R-tree. Okay, so now I will talk about the R-tree. So the basic idea of R-tree is the points are contained in a box. So let's say there is a kind of dense area of point. Think of the box which contains those points. And this box formalizes the tree structure. So there are some boxes and there is another parent box which contains those boxes. So I will show you a picture. So let's go with this example. So let's say, firstly, I would say in this R tree, points are included only in the leaf node, which means that, the leaf nodes are represented as gray boxes, so point exists only these gray areas only. That being said, there's some point here, there's some point here, there's some point here. So if user is interested in searching around this area, or I should say, let's say this area. And because I have the kind of range of latitude, or I should say range of x and y of A, when user searches with this area, it checks which boxes or which box has the overlap with that search area. And in that case, let's say it has the overlap only with box A. In that case, query engine now checks the data point which are contained in the node A. So that's the basic idea. Okay. But as you can see, and as I said, it forms the tree structure. So in case of A and B, there is another box which contains N, and it has to check. Let's just say, yeah, there is a parent box which is N. So why do we need it? It's because when I form the parent box N, what I can do is, let's say I'm searching for around this area. In that case, if there isn't a box N, I have to confirm that A doesn't overlap and B doesn't overlap. But now, because we have the box N, what I have to do is just confirm that the box N doesn't overlap with the search area. And I can completely forget N and the child nodes A and B. So in this three, example, I can say, in this tree image, I can say I'm searching for a specific area, and it first checks T and U. If T doesn't overlap it, which means the search area is not in this area. So I can completely forget the subtree and reef nodes below the node T. So I can say trimming. Trimming is very efficient with this tree structure. So that's why we need the box, parent box, and parent box, grandparent box. Yeah. So yeah. Okay. So that being said, I will show you some example queries. So let's say, as I said, I'm looking for the 10 miles around this area, around here. In that case, let's say around this area. So in this case, from the 10 mile, I can know the X range and Y range, X range and Y range. And after that, from that X range and Y range, I will start from here. So T has the X range, Y range. U has the X range, Y range. And of course, because I'm searching here, in this case, it overlaps both of them. So which means that I have to check both T and U. So maybe I should be clear on this. So boxes, reef boxes doesn't overlap, but parent boxes may overlap. So in that case, I have to track each path. So in this case, I go to T, and then internally, as a child knows, it has NPQ. And check N X range Y. This node has X range Y range of N, and X range Y range of P, X range and Y range of Q. So it compares with this searching area, searching ranges. And N doesn't overlap, so I can forget it. P doesn't, and Q does. So I have to track only Q. And when I go down Q, because I'm searching for around this area, again, I compare the search area with the X range, Y range of F and X range, Y range of G, and only G overlaps. So the data point in G is a concern, and I have to scan it. And when I go to U, the same thing happens. For 3, I can say S cannot be S can be skipped, trimmed, and for R is around here. It overlaps, so I have to go up, down, and HIJ, I doesn't overlap, so trimmed, J doesn't, so trimmed, and H is my concern. So I can say I have to check the data point in G and H. So actually, what happened is, to search this area, the database engine only takes a look at all the points in this area, H and G. Of course, this is much more, efficient than the example I told before about the B tree. So that's the kind of, benefit of using our tree. Okay, I will show you another example. So let's say I'm searching for our restaurants in California. So in that case, California state is not round, so it's a kind of complicated form. But still, I can get the X range and Y range, and does this. Yeah. So in a completely same way. Of course, I can say if the area is, more like the rectangle shaped, it's more efficient. Yeah. Of course, it's like this, let's say, river, like the stripe shaped, like, diagonal. diagnostic, it isn't so efficient because it checks only the X range and Y range. So maybe I should rephrase. Let's say there is a such area. Maybe it can be circle, or maybe it can be strip like the river. In either way, the query engine finds out the you know rectangle which completely covers it, and then compares that rectangle with this tree structure and trim unnecessary paths and go down to the leaf node, which overlap with the search rectangle of the search area. And as I said, that leaf nodes is not necessarily only one. Maybe there are two or maybe three leaf nodes, which overlaps with the search, rectangle. Okay, so this is the R3. So I will talk about the pros and cons. Okay, so for R3, I'd firstly say this R3 is balanced. So I will tell you why. So in this case, as I said, when the R3 is built bottom up. So let's say there's so many points here and there are many points here. And it creates the parent box. So firstly, I can say when building the R3, it can be the balanced tree. So it's the problem of how the database engine creates the tree in a bottom-up way. So let's say, I think this is a good example. When the database engine creates the tree structure, as you can see here, P contains 3 nodes, but Q or maybe N contains only A and B, 2 nodes. This is because when I take a look at this area, P, C, D, E are dense, and A, B are relatively less dense. So in this case, because P is more dense, this area is more dense, P contains 3 nodes, child nodes. So I can say if there is an area which has many boxes contained, the parent box has many child nodes. If there is an area that there aren't so many boxes, that parent node contains only less child nodes. With this kind of adjustment, the whole tree structure can become, balanced. So I can say the query performance is stable. Okay, so next, actually this is same. So button handling dynamic data point. So because like quad tree, this is a tree structure, and in the tree structure, what happens is that if there is a point in here and it moves here, so in that case, I have to create a new box. And of course, this box has to be, included in the parent box in this level. So I have to adjust the parent box 2 and then maybe grandparent box 2. So of course, the data point is moved inside of the leaf node. There's no problem. But is the data moved out of the leaf node area, and that is, database has to restructure the tree. So I can say this R3 index is the bothered handling dynamic data points. Okay. And I will talk about one strong point of R3. This can handle polygons. So polygon is not the data point. So can handle not only points but also polygons, I would say. So polygon is like the California state, form of the California state, or maybe form of the river, form of the park, or something like that. Yeah, that's the point. So what happens is that, and sorry, what I'd like to do with polygon typically is, given the area, returns the polygons or point included in that area. Yeah, and now that polygon, like park, is considered as the smallest box, smallest rectangle, which contains that park form. Yeah. So if the park is look like this, oh sorry, G is the minimum containing box. And now, database handles this park as that. So in this case, what should I say? So in this leaf node G, not only point, but a rectangle who is completely contained in this G area. And park is represented as that. So in this way, just like the same way as a point, I can know if the park is included in the search area. So of course, because I'm talking, I kind of approximated the park form with rectangle. If the search area is the edge of the rectangle and park isn't actually, it is possible that park actually doesn't overlap with the search area. So in my understanding, finally, in node G, the database engine has to check if the exact forms of the park has the overlap with the search area. But, narrowing down to node G this completely works by considering this park as the, minimum containing boundary box. Okay. So that's how this R3 handles polygons as the data input. Oh, I just want to emphasize that I said polygon, but of course, it is possible that the data input, data point in the database, can be polygon. So in that case, as I said, database index treats that polygon as the minimum boundary rectangle containing rectangle. And of course, the search area can be not rectangle. In that case too, database, query engine takes the search area as the containing, rectangle, minimum rectangle. And in either case, after the filtering is done, it has to check if exact form of the data input or query input has the overlap with the query area or input data. Okay, so I will talk about the geohash. So as I explained before, geohash creates the kind of hash value from xy, or I should say latitude, longitude, and store that hash value in the B tree. And what is that hash value? So I will show you with this. So firstly, let's think of the map. And map is divided into 4 areas, and then recursively sub-area is divided into another 4 sub-areas. Yeah, blah, blah, blah. And as you can see, each, I should say, kind of reef area size, all the reef area sizes are the same. Yeah, unlike the quad tree. So with that being said, yeah, these numbers, hash values are stored as a B tree. So let's say I'd like to search the point which is around this area from this point and radius, very small radius. In that case, database has to check, the data point whose hash value is 31. So it can find the beginning of the data point whose hash value with log n time with B tree, then scan all the data point in this 031. Do the linear scan. But obviously, it has to check only this 31 area only. So the area to be kind of linear scanned is much smaller than the case of quad tree. Okay, so that's the geohashing. Okay, so I summarize pros and cons. So firstly, I would say I can use the B tree internally. So this is mature technology. So of course, let's say if we'd like to use the Redis geohash, of course we don't have to calculate, we don't have to calculate the hash value in the application layer. Redis internally does it. Yeah. But let's say we'd like to tune the database very much. In that case, maybe we'd like to do it in the relational database in a custom way. Yeah, but in that case, the application layer should calculate the, hash value. Yeah. So that's the first strong point. And second strong point is good at handling dynamic data point. This is because when point moves from here to here, let's say here to here, all the things which have to be done is update the, of course, x value and y value, or I should say latitude value, longitude value, and then update the geohash also. Hash value also. So just updating 3, column values. That's it. Okay. And as the weak point, I would point out that there is a problem which is called boundary problem. So boundary problem is, let's say I'm searching for this area and the center point is here and the radius is around this size. In that case, because it overlaps with 0 and 2, the database has to check not only 30 but also hash value 12. So that's it. And of course, let's say the center point is here and the radius is really big, like this area. In that case, database engine has to carefully check which hash values area has the overlap with the, circle of the search area, and check all these, check all the data point which has those hash values. Yeah. So that's the boundary problem I have to take care. And I want to quickly point out that this geohash like this doesn't, takes the cover of the earth into consideration. So if I try to, and definitely I should, because I should take the cover of the earth into the consideration when I, create those small areas. Actually, there are some technologies which handles it. So firstly, I can say S2 index. This is a kind of geohash index. This is developed by Google, handles it. So in S2, each area is shaped like this. Not the rectangle, but yeah, similar to rectangle. And also, Uber developed the geohash index named, H3, and Elasticsearch uses it. So each area, as you can see, is hexagon, and each hexagon has child hexagon. Yeah, so that's the H3. Okay. Okay, so yeah, that's it. So I will quickly review what I explained today. So today I talked about the geospatial indexes. So the primary use case of geospatial indexes is like the query pattern, like find all the data point, which is up to let's say 20 miles from the center point, XY, or longitude, latitude. So for this, geospatial indexes exist. And I introduced 3 geospatial indexes. And 2 of them are tree structured. One is quad tree. So quad tree, divides the area into sub-rectangles, 4 sub-rectangles, and it happens only in the dense area. I mean, for the dense area, for the dense place, the rectangle is subdivided into 4 recursively. Yeah. So as the weak point, the reef of the dense area is quite deep. So I mean, the search for the dense area is not efficient and performant. For R3, so yeah, this is the tree structure, but it has the box, tree of boxes. Yeah. So for this one, query performance is stable because this is a balanced tree, which is built bottom up. But yeah, and also this can handle not only points, but also polygons. If the polygon is kind of inserted as the data, the database engine considers it as the smallest containing rectangles box. And in that way, let's say there is a query if, let's say, a park is included in the specific area, that kind of query can be handled too. But for quad tree and R tree, because these are tree structures, they are bad at handling dynamic data point. If the point moves dramatically and maybe intensively in the index, in the database, it has to restructure the tree, which takes so much cost. Okay, and another geospatial index I introduced was geohash. So this geohash is very simple. So internally, it creates the hash value from longitude, latitude, or XY, and creates a B tree on that hash value. So, yeah, the good point is it can use the B tree internally, which is mature technology, so stable, and also good at handling dynamic point. It just when there is an update query of the data point, database has to update XY and also the hash value recalculated. Yeah. But there is a kind of boundary problem, so I have to be taking care of that. Okay, so I will talk about the use cases in the system design. So for Uber, we should use geohash because in Uber, drivers, obviously moves around the area, so the data point is dynamic data. So we shouldn't go with R3 and we should go with geohash. And as I said, code tree is not so frequently used currently in the production data system, in my understanding. So I basically compare R3 versus geohash. Yeah. And in case of Uber, geohash is better. And in case of Tinder, actually both of them works. But maybe geohash is a little bit better. So I would say, in case of the Tinder, so let's say there is a user. He in his app, the girls who are, let's say, up to 30 miles, according to his preference. The girls girls who are within 30 miles from his center position are displayed in the kind of suggested users. But in case of Tinder, Tinder system creates the suggested profiles, kind of stack of profiles with daily cron job, not as the query not on spot. So actually the query can take much time. And also, as I said in the Tinder's video, Tinder's place update is not frequent actually, not like Uber, because in Tinder we don't need the accuracy and fine location like Uber. So the update of the data point is not actually frequent compared with Uber, but still there are, and according to where the if I use the PostgreSQL PostGIS extension, and if I put the location data in the user table, it's not a good idea because update queries takes so much time. But if I separate the data point into another database, I think, or maybe another table, I think it works. Yeah. Okay, so that about the Tinder. And lastly, I will talk about the Yelp. So Yelp has so many restaurants in the area, and the user searches the restaurants according to the current location, or maybe specific location, or maybe with the city name or state name. And I can say in Yelp, restaurants don't move so often, obviously. So I don't say they're dynamic data points in Yelp. And when I think of this, R3 and geohash, I can compare them exactly, especially from the perspectives of the read performance. And read performance-wise, R3 is better. R3 overperforms GeoHash for the read queries. Yeah. So I would go with R3. Yeah. So because the reason why read queries perform better in R3 is R3 has the kind of flexible shape and size of boxes. So the data point to be scanned is quite there aren't so many redundant, or I should say kind of I mean, the number of data points to be scanned, linear scanned, is minimum. But in case of the Redis, according to the shape of the search region, search area, because of the boundary problem, it has to check so many redundant, data points to be linear scanned. So that's worsens the performance of GeoHash. Okay, so that being said, I finished my today's system design practice. Thank you so much. Bye.